So as I've mentioned, a lot of you guys sent back, basically sent me email saying, "Oh God, oh God, oh God, I need an extension." Although you were a lot more, even though you were feeling that, you were a lot more calm and persuasive. I have extended the current homework to Friday. I will probably be posting another assignment, one that I feel is easier on Wednesday, which has to do with trees. So, and your next time lab will be not this week, but next week. Now that timed lab, I am happy to, that's going to be 50 points of that will be on trees, and 50 points of those will be on heaps. And I just finished doing the videos on heaps, and they are really simple. About 30 of the points you should be able to grab just by remembering, oh, he said those were in the slides. I can go to the slides and get those equations, and those are super easy to implement. Like, we're talking really easy equations here. So just keep that in mind. So it's not really, so heaps aren't really too bad. The next thing is, I'm going to delete this and rewrite this in front of you guys because it's worthwhile for me to do that. So because you guys need it, so again, time lab next week, we'll work on time lab next week. That means that your exam will probably not be like on week 10, but probably like week 11, right? And that will probably go, depending on how far we get, that might include hash tables, okay? But it just really depends on how far we get. So we're gonna go over, I'm gonna help you get started on the 8 queens problem if you're still struggling. And we're also going to go over some of the content in the video, specifically adding, removing nodes today, since you guys might not have had the chance to watch them, right? I post the videos. I understand that midterms are only just finally stopping, right? Right? So, I keep that in mind. All right. So if you're having trouble getting started with the 8 queens problem, it's part of what you need. So it's because you might not be doing things necessarily in the easiest order for yourself, right? So if we go to the assignment, I have assignments. Let's go ahead and take a look. And let's just review. So I'm going to assume that everybody's taken a look at this problem at some point, right? And here's our, let's go ahead and fit with, right? Here's my problem. Solve board position. Now, what position is, again, depends on your on our particular problem. It's row, column, and Sudoku. Here, because of the hint I give you, I mentioned that you want to consider this, that each queen is basically, each part we're solving is a particular column. Where do I put so I given a column, where do I put a queen in a safe spot in this column? So the way this algorithm says it works is if this position is such that there's nothing left to solve, return true. In other words, if I'm done solving things, return true. If I'm done with the board, return true. We'll figure out how to do that later. Okay, for each possible choice. Well, if I'm trying to figure out where in each column to put a queen, then the choice is the row. Okay? So if it's a valid row to put my queen on, I put my queen there. And then I solve the next column. Right? I recursively call the next column. Now this part's the tricky bit, but once I draw it on the board, I generally find it becomes a bit easier to understand. Which is where we call the next board, and if it returns true to me, then I return true. If I got to the end, in other words, then I basically if we get to the end over here, this true will return true to this, which will return true to whoever called him, and it's basically this cascade of return true calls. Okay. Now, if it wasn't valid, here I actually do need to unmark. I need a clear choice. I need to pick up the queen, right? If the choice was valid, I put it down. If it was and if it could do it, if I couldn't, if that didn't work, if I put it on a queen, it didn't work, I have to pick up that queen over here. So that's one stumbling block. Here, because I adapted this from a generalized algorithm, and most algorithms you clear your choices over here. With the 8 queens, you've got to clear the choice that you made where you put the queen down basically over here. Okay, so what I'm going to do is I'm going to run through this algorithm while this is up here, and we are going to just simply run through this algorithm on a 4x4 chessboard, right? A 4 queens problem, if you will. Right? Mainly because, and I'll use this little crack to my advantage here. So, mainly because you can solve the 4 queen problem using this algorithm in a very reasonable amount of time, whereas 8 queens is a pain in the butt using this algorithm by hand. Right? So here's my 4x4 chessboard. Okay? Okay, so the way we start is that we start by calling the first column, right? And I ask for each row in this column, is this a safe place to put a queen? Right? And it is, right? There's no other queens on the board, right? So it's kind of safe. But how do I check if it's safe? Well, we'll get that onto the next one, right? So I call the next, but for each possible, I choose the first row. That first row valid? Yes, it is. Go on to the next. Put down the queen. Solve column 1, right? So now I solve column 1. So is my position such there's nothing left to solve? No, it is not. I'm still on a column, then I need to put a queen here. For each possible choice, for every row, is this a valid choice for where to put a queen? No. How do I know that? Well, I have to check different directions, right? I know there's a queen in the same row of me, so I can't put it there. Now, as I've mentioned in the video that hopefully you watched on this program, I only need to check going this way, and going this way, right? Because if I'm working one column at a time, I don't have to check vertically because there's not going to be a queen already there. And I don't have to check anything in this direction, or this direction because I'm placing queens in this direction, so there's not going to be anything in front of me unless something goes horribly wrong. So I only have to check 3 directions. Okay, so I check that way, there's a queen there, can't put it there, but this is a valid choice, so I put a queen there and call to solve column 2. So I go on to column 2. Can I put a queen here? No. Here? No. Here? No. Here? No. So clear any choices, there were no choices made, so I return false. So now this call, so now we're back in solving column 1, and it just tried to solve column 2. It did not get back to true, it got back false. So we're at the end of this, so that wasn't a valid, so while it was a valid choice, it did not provide a solution. So we got a false. So we pick up our queen, and we go on to the next possible choice, which is this. Okay, so I put a queen here. Okay, so I call solve column 2 again. Okay, put a queen here. No. Here? Yes. Also need a new dry erase marker, apparently. I've got an entire bag of them, and now I need to figure out which ones are actually good. It's the entire bag, so we're just going to go and, winnow through them. So, is this space good? No. Is this space good? Oh, wow, this one actually is considered amount of good, even though it looks smirched. This space good? No. This one? No. This one? No. This one? No. So, solving column 3, that returned false, which returned, so here, we're back in column 2. I have to pick up the queen. Can I put a queen here? No. Can I put a queen here? No. Return false to column 1. Column 1 goes up. Okay, for each possible choice. So I went through all my possible choices, so I have to return false to column 0. Okay, column 0 says, well, I've still got 3 squares to check, so I'll go on to the next one. Hey, what do you know? It'll work. So now I call solve column 1. Can I put a queen here? No, 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 yes. Can I put a queen here? Yes. This won't work, this won't work. This works though. So I call solve column 4. So now solve column 4, that's like right over here, right? That's out of bounds. So we'll use that as a terminating condition. There's nothing left to solve. We return true. Okay? So, since that returns true, well, column 3 gets back that solving column 4 returned true, so we return true to column 2, which returns true to column 1, which returns true to column 0, which returns true for the whole thing. Now, point that some of you have asked, you are looking for a solution, not all of the solutions. There's like 92 solutions for the 8 queens puzzle. You're looking for basically the first solution you stumble upon. Okay? and like most of them are rotations of each other, but basically you're not trying to solve all of them. If you were trying to solve all of them, whenever you got to basically at here, you would essentially just print out the board, right, and then continue, and then return false, and then continue going until you got through all possible combinations that you checked. And that takes a bit. All right, so how do we code that up? Well, believe it or not, the way you want to start coding this up is that we don't start by coding up the solve method. First thing we start coding up is the valid, because that's something to test. That's something we can test, and we can have like it partially working, like saying checking just the rows, okay? Just checking that that part works, and then you can check that the recursion works, right? And so we can move on from there. So we can start with a partial solution. So first thing I'll code up is I'll code up my public static Boolean, and I like to call mine is valid rather than valid, but that's just me. And that will take in what does it need to know to work, right? I'm trying to say, okay, is this a valid place to put a queen? Well, I have to know for the board, right? On this board, I want to put a queen in this row and this column, right? That's where I want to put a queen. And by default, we'll return true, right? A space is valid until proven otherwise, right? And I'm recording this so you don't, and this will be uploaded, so you don't have to be in such a frenetic pace to copy it down if you're worried about that. The classes where I went over this yesterday, that's already uploaded online, so you can check that out. So return true, and right, what do I have to do to check if something's valid? I have to check if there's something in the same row as me in the upper diagonal and the lower diagonal. Now, one thing that you want to do is make those 3 separate checks, and I might as well make those individual methods just so that they're discrete and easy to test. So I'll basically create a public static Boolean is row valid with an int board, int row, int call, right? And again, I'll return true by default. And all I'll do is just simply check if there's any queens to the left of me, right? And I use the 1 to indicate the presence of a queen. So for int I is equal to 0, and this one's going to look a little weird, but it will make sense once you see it once you see the fullness of it. So for int I is equal to 1, column minus I is greater than or equal to 0, I++. That seems a bit weird, right? But here what I'm going to do is that I'm going to I'm going to say if board row call minus I equals 1, return false, right? If we see, so this is saying over here, if I see a queen in the same column. So what is call minus I? Well, it's 1 to the left of my current position, then 2 to the left of my current position, then 3 to the left of my current position, then 4 to the left of my current position, all the way until I go out of bounds and I don't bother checking out of bounds. The hardest part about checking this, honestly, I find the hardest part about these things, about these boards that we have to solve for both this and Sudoku, is making sure you don't go out of bounds. And my hint to that is you can make these things extremely complex. You don't actually have to work up, you can put whatever you want here as your while condition. Like I could make a AND clause, right? And I could check like row being modified and column being modified with an AND clause here. So if board row column minus I is equal to 1, return false. So if we see a queen, we return false. So if not is row valid, so if the row isn't valid with board, row, and column, ooh, that's pretty nice, it filled in all those. So if the if not is row valid, return false. Right, so if none of those are false, so if this isn't a good row to put a queen in, we return false. Now, what I can do as we add more as we, so that's the only valid check I'm going to put in here, right? Checking the upper diagonals and lower diagonals, I'm not going to code up here. But as I code, if I code them up as separate methods, I can just do an and call over there and call them in the same method, right? Right? Right, but this works for right now, right? And if all I'm checking is the row valid, then the way algorithm is going to look, well, let's think about that. If I'm just checking to make sure if this is in the same row, well, there's no other queen in the same row. There's a queen in the same row over here, so I'm going to go on to the next row, which is fine. There's no queen over here in this, sorry, there's a queen in this row, there's a queen in this row, there's no queen in this row, and so on and so forth until we get over here, right? So if we use this as our valid method, then this is our expected output, right? Kind of like an 8 rooks problem or 8 castles problem now, right, since we're not checking diagonals. But now if we program the solve method and we get this, then we know our solve method works, and the only thing left to do is to program the is valid, and that's actually something kind of familiar, right? We're just checking a 2D array for values, okay? And notice that I'm starting at row column and just radiating out from that position, okay? That's the way you want to do it. All right, so now let's go ahead and do the solve method, and fortunately this is you know, monospaced. You know, this is essentially been typeset as typewriter over here, so I can copy this from the PDF. Other stuff, it's harder to copy from the PDF, but the code is fairly easy to copy. Actually, I'm not going to work on that yet. First thing I need to do, as I mentioned, is I need to test it. I need to test this. So how do I test my valid method to make sure it's working? Well, I have to make myself a board. How do I do that? Let me just make myself some more space over here. Int double array board, and rather than making it like declaring it like this, int 8, I want to actually have a view of what I'm doing as I test it, right? Rather than making a new int. I forgot the new there. I'm actually going to manually create it. So I'm going to make an array of 8 arrays with 1, 2, 3, 4, 5, 6, 7, 8. So that should be 8. Yep, that looks like 8. Put a comma here, and then behold the magic of copy and paste, right? So move this. Whoops. And one more. Remove the comma over there because there's nothing after that. And then I have to tell Java to end the line. So there's my 8x8 board. That's my empty chessboard. And the reason is that basically I want to test to see if my is valid works. So I'm going to put a queen here, and I'm going to put a queen here, right? And I'm going to put a queen here, right? Just to simply check everything. So sout is valid board row 0 column 1. Right, that should return false because I'm checking is this a safe place to put a queen, and there's a queen here to the left of it. So that should return false. Make sense to everybody? So that works. And row 1, column 1, right, the next row down, that should return true. I mean, this is fairly simple. I don't feel like any pressure to do any more tests on this. So now I can move on to the solve method, right? But now we know the is valid work. But here you would want to test all your is valid method to make sure that it works. So now I can grab the solve method. And whenever you get stuck, just simply, test the components as best you can. This is why we do things in methods, so that you can test the individual methods themselves as atomic units. So here, put that down. So here for int board, so this should be public static Boolean solve, right? Board, and we're asking to solve for a particular column, right? If the position's nothing such that there's nothing left to solve. So if a call is greater than or equal to board.length, right? If column is out of bounds, then we're done. So for every possible choice, which would be for a row, so for every possible row, let's see. So for every possible row is less than, and again, we're assuming the board is square, board.length. If is valid, and that needs 3 variables. That needs board, row, column. So if it's valid to put a queen there, we'll put a queen down. How do we put a queen down? By putting board. Sorry? Row col. Yeah, column's up here. Right? So for every possible row, we can put a queen down, is the idea there. And yeah, let's go ahead and there we go. That indentation's kind of been fixed. Kinda. Code. There we go. Board row column is equal to 1. Put down a queen. That should be col. Whoops. So we put down a queen. If that position solves the board, then great. We return true to whoever called us to say, hey, that position solved the board. Yes?
What was that command you used to clean up the formatting?
Control Alt L on this, but it was reformat code. And then if I can't do that, if I can't use that there, then I do board row column 0. Right. Sorry. Nope. That should be over here. Inside that if statement. So now what I can do is I can test this. Right? And first let's get rid of I'm going into insert mode and replacing all these zeros, so I can start with an empty, pretty sure we're like the reason that insert still is a thing. So now let's go ahead and do solve board, start at column 0, and then we need to print out the board to make sure it works, which is actually annoying. So for each int double integer row, so for each integer array, not double integer, but integer array row in the board, sout arrays dot toString. The arrays class has a bunch of methods, one of which prints out an array in a nice format. Arrays toString row, and this will let us know if it works or not. And so we got the ones going down the diagonal that I said we would get. Right? So now we know that we've got a working recursive method, right? That we just simply that I quickly went through, right? But I didn't change. But I simply did all the changes that I said it would. Like for each possible row that we could put down, we check if the row column is valid. If so, we put a queen down, and then we try to solve column plus 1. If that works, great. If not, we pick up our queen. And our base case is that if we're done solving things, if we're at a dead end column. So that's basically where you go with the 8 queens method. Now for Sudoku, you have it's similar. The way I would suggest starting Sudoku is writing your isValid method, and I would just write it so that just the row has unique values. You don't care about the columns or your 3x3 grid, right? You just make sure that just your row has the unique values 1 through 9, right? That there's no repeats in any single row. Then you add, okay, rows and columns, and then you go rows and columns and that 3x3. Now, how do you solve the 3x3 thing? And the answer is you use division. So if I look over here on Sudoku, now Sudoku, the New York Times page is great for Sudoku because they have this just nice looking puzzle and it's nicely formatted and stuff, right? We look at this and it's a 9x9 array, right? But we can also view this as like it's a 3x3 of 3x3s, right? Right? It's 3 big squares by 3 big squares. And one of the keys to solving to figure out, okay, are there any repeats in my 3 by 3 square, is that you go, let me check all the values here, then all the values here, then all the values here, right? You treat your own just check that little 3 by 3. Now the key to figuring that out is for a given square, what is the top left corner of my 3 by 3 square? Because if you can find your top left corner, you can check these values, then you can start from here and basically say, okay, here's my row, I'm at index row corner, column corner. I want to solve column corner plus 1, column corner plus 2, then row corner plus 1, column corner plus 0, row corner plus 1, column corner plus 1, row corner plus 1, column corner plus 2, and so on and so forth, right? So basically, it's a nested for loop that goes through the values 0 up to and including 2, based off of what your corner values are. So how do you find the indice of that corner? The answer is you want to use division. Let's go ahead and just take a quick look. If I look at this square, this particular square, it is row 7. And it is column 4, row 7, column 4. Now if I divide 7 by 3, I get 2. 1, 0, 1, 2. And if I get row 2, and if I divide, if I add through, if I divide by 3 again, I get 1. If I divide the column value, which is 4, by 3, I get 1. So if I divided the row and the column each by 3, and I got row 2, column 1. As far for the big, for the 3 by 3 square. Right, so if you divide the current squares, row and column by 3, you get the big square that you're in. And then if you know what big square you're in, you can figure out you can figure out the index of this square or 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 this square. Sorry, I got a bit distracted there. My phone started ringing in the middle of that, so that was just a bit distracting, trying to who's calling me at the same while I'm trying to explain this. All right, but that's as much hint I want to give on the Sudoku. Now